In most cases, tools that we use that have lenses are going to have more than just one lens. For example, a microscope, a telescope, you name it, a camera, and so on. So because of that, it's very important that we learn how to handle, how to work out problems that involve more than one lens. Okay, let's take this special case where we have two double convex lenses. The idea is the image from the first lens is going to become the object of the second lens. Okay, let's think of that. Let's think of what that means. So I have my lens, I have my object. So that object, since the light being reflected off that object, is going to meet that lens before meeting the other lens. So that object is going to be an object of only that lens. Now, this is DO for that object. And then we can use our lens equation, 1 over f1 for lens 1. Let's call it DO1 because we are dealing with lens 1. So it's going to be 1 over DO1 plus 1 of DI1. And that's the way we can find the image. Okay, we can do it here also graphically. Okay, remember the principal axis, one parallel to the principal rays. One light beam that's parallel to the principal axis is going to pass by the focal point. The one that's passing by the focal point is going to come out parallel to the principal axis, and the one through the center is going to continue straight. Of course, I'm not doing these ideally, but that's the idea. So in this particular case, we are going to get an image somewhere here, inverted and real. And this is going to be my DI. Remember here we have an object that's beyond the focal point of a double conversion lens, and it looks it's beyond the focal point, but not too far from the lens. It's not beyond twice the focal point. So we get an enlarged, inverted real image. Okay, now that's my DI1. This image, okay, let me change color. This image, I don't like that color now. Let's go to red. So this image is going to act like the object for the second lens. So this is going to be DO2. And this is what where you need to be careful. A lot of students, by thinking that the object, the image of the first lens becomes the object for the second lens, they decide that DO2 is equal to DI1. You notice here from this graphic, they're not. DI1 is the image distance relative to lens 1. DO2 is the distance from where that image got formed to lens 2. And usually we have to figure it out, depending on the situation. For example, if they gave us the distance separating the lenses, for example, if we know this distance, then in that particular case, DO2 is going to be equal to D minus DI1. So you have to figure it out one case at a time, depending on the geometry you are given. Now that we know what DO2 is, we can write the lens equation for the second lens. 1 over F2 is equal to 1 over DO2 plus 1 over DI1. And that's the way we can find DI1. Of course, here I can follow through and try to do the same thing graphically like I did there. So a line parallel to the principal axis is going to converge into the focal point in the other side. and one that's passing by the focal point is going to come out parallel to the principal axis in the other side, and one passing through the center is going to continue straight. So this is actually my final image. And this, let me erase it. Wonders of technology. This is my DI2. Notice here, the first lens resulted in an inverted or flipped image that's real and enlarged. And then the second lens resulted in an image that is again flipped and real, but it is reduced. The final image, because we had twice the flipping, ended up coming out upright. Okay? This is one example of how to handle multiple lenses. I have another example here. It looks very much the same as the other one, but graphically, I'm going to do the same thing. This is my DO1, and let's try to find graphically where DI1 is going to be. So I'm going to draw the line parallel to the principal axis and make that pass through the focal point in the other side. And then one that's passing through the focal point here is going to come out parallel here. And then one passing through the center is going to continue on a straight line. This is where my image forms. So this is my DI1. I'm not writing anything here, but remember, it's the same equation as we had here. There's nothing different there. Okay, let's go back to a different color. Like last time, this is going to be DO for the second lens. And we have to figure it out depending on what else is given for us. And then we can try to find the image resultant from that lens by using the equation 1 over DO2 plus 1 over DI2 is equal 1 over F2. However, before going further, we notice here that this object is within the focal length. By the way, the focal length of the lens is drawn incorrectly here. It's supposed to be here, the same as that point, F2. I just noticed that. It's within the focal length of the lens. Because it is within the focal length of the lens, we know that it's not going to result in a real image. But anyway, let me choose another color so we will not have everything colliding color-wise here. So I'm going to try to use the ray diagrams. So if I start with a beam parallel to the principal axis, that beam is going to go through the focal point. Now, a beam that looks like coming from the focal point, it's going to continue straight here. And the beam through the center of the lens is going to continue straight as well. Notice these beams are not going to meet there. However, I'll choose another color again. They are going to look like they are coming from here. So in this particular case, it's going to look like they are coming from this purple image here. So that's actually, so it is, this image is in the same side as the object relative to lens 2. This is my di2. If you do the calculations correctly, you should find it negative. And you notice it's in the same orientation as the object. Both of them are inverted. So the second lens didn't flip the image. And here we go. Okay. One last thing to discuss about multiple lenses is the fact that the magnification of multiple lenses is just the product of individual magnifications. For example, if this lens has an object H01 and results in an image HI1, remember magnification 1 for lens 1 is going to be given by HI1 over H01. Now, using the same terminology, this is going to be HI2, but this is going to be HO2. You notice that actually HI1 is equal to HO2. Now the magnification of lens 2 is equal, using the definition again, HI2 over HO2. The overall magnification by definition should be the final image height, HI2, over the original object height, HO1. You notice when we make the product of M1 times M2, what we have is HI1 over HO1 times HI2 over HO2. However, because HI1 is equal to HO2, these two cancel out, and we are left with this. So there's the proof. If we have more than 2 lenses, you just continue the product. If I have 3 lenses, so M is going to be M1 times M2 times M3, and so on. And remember also the magnification for each lens. For lens 1, it's going to be minus di1 over do1. For lens 2, it's going to be minus di2 over do2. That's important.